All right, so I want to continue talking about plastic properties of materials, and in this case, we're going to talk about what's called ductility. So, in general, ductility is a measure of plastic deformation at fracture. And so that refers to how much it changes shape, right? So that's going to be strain. So a material that doesn't have much plastic deformation, like this blue material here, right? It's mostly linear, mostly elastic, and so you just have maybe a small amount of plastic deformation. And so the total amount of strain when it fails or at fracture, point B, right, at point C here, isn't very much. As opposed to a ductile material, which we've kind of seen in the last couple of modules, where we have that elastic portion, but then we have a sizable amount of non elastic plastic behavior. And so when it fails at B, the strain is much higher, right? So there's been a lot more permanent or plastic deformation. And so in general, we would refer to a material that has a lot of strain or plastic deformation at fracture to be a ductile material because it exhibits, again, significant plastic deformation, and one that doesn't exhibit much or any plastic deformation as being brittle. So those are kind of the opposite ends of the spectrum. So let's talk about how we quantify and measure ductility. And so we do it, the easiest way is to look at the percent elongation. And so we can define the percent elongation as this. So percent EL for elongation, and that's the final length minus the original or initial length over the initial length. And if this equation looks familiar, it's because this is effectively strain, right? Difference in length over an original length is strain. And so it's basically the strain at fracture, right? When the length is at fracture. And then the only difference besides that is it's strain multiplied by 100, so it's percent, right? But it's effectively strain at failure multiplied by 100. And so, again, a material like the green one here is very ductile because it has a higher percent elongation than this smaller, the more brittle material that has a smaller strain at failure. And so, again, the length original before it breaks, or before the test, and then the final length of the material after it breaks. So that's how we calculate elongation. We can also calculate it. Ductility uh, is the first measure is percent elongation, and that's the most straightforward way. But as you know, Poisson's ratio relates the axial strain to the lateral strain. And so the lateral is related to the area. And so we can also define ductility by a reduction in area. And so that's the final area here. So percent reduction in area, or percent RA, is the original area minus the final, and then over the original area. And the reason we've switched this is because now this is to avoid a negative sign in that equation. So this is obviously another measure of ductility, but it's not as common as the percent elongation, just because measuring the length is a lot more straightforward than area in most cases.